The Large Hadron Collider (LHC) is the world's biggest laboratory for scientific experiments. LHC and its experiments are unmatched in size, complexity, participation, and achievements by anything ever built and operated by scientists previously. The LHC experiments on collisions of high-energy particles seek to unravel the mysteries of the evolution of the universe immediately after the Big Bang. In a major breakthrough, scientists at LHC have confirmed the existence of Higgs boson, the particle that imparts mass to other fundamental particles. The discovery of Higgs boson ranks among the most important achievements of science in modern times. Scientists working at LHC have now moved ahead with experiments which seek to verify their theories and predictions on frontier areas of research like dark matter, antimatter, and supersymmetry. The gigantic LHC project is implemented and operated by the European Council for Nuclear Research, CERN. CERN is an intergovernmental organization initiated by 12 European nations who were trying to aggregate their scarce resources for scientific research immediately after the devastation of Second World War. Today, CERN has 22 European states and Israel as member states. 8 countries, including India, are associate member states. Japan and the United States hold observer status with respect to the LHC. Experiments at CERN are international collaborations in scientific research. Over 600 universities and scientific institutes participate in the activities of CERN. CERN was established in 1954 and it is completing 70 years of cutting-edge experiments and research in fundamental physics. CERN is based in Meyrin, western suburb of Geneva in Switzerland. At CERN, scientists explore the underlying structure of the universe by studying the collisions among high-energy particles. World's most complex scientific instruments, particle accelerators and particle detectors are used for this purpose. CERN has a number of particle accelerators in its accelerator complex. Linear accelerators, proton synchrotron booster, super proton synchrotron are among these particle accelerators used for various research activities. A particle accelerator is a machine that increases the velocity and energy of charged particles. This is accomplished by making the charged particles pass through a region where an electric field is used for imparting electrical forces to them. Accelerators can be linear or circular in geometry, depending on the trajectories chosen for the particles. Accelerators can also be classified into electrostatic accelerators and electromagnetic accelerators. In electrostatic accelerators, static electric fields are used for accelerating the charged particles. The earliest accelerators like Van de Graaff accelerator and Cockcroft-Walton accelerator were of this type. In electromagnetic or electrodynamic accelerators, oscillating electromagnetic fields are used for accelerating the charged particles. Most modern particle accelerators are of this type. In accelerators with circular geometry, the charged particles go around the same circular path again and again, increasing the velocity and gaining energy at each circular turn. Acceleration is done by making the charged particles pass through a cavity with an electromagnetic field in its path. Radio frequency cavities or RF cavities are used for this purpose. A cavity is an empty metallic chamber in which the intensity of electric field is built up by resonance. In accelerators with circular geometry, magnetic fields are used for steering the charged particles into the circular path. More the velocity of the particles, higher is the intensity of magnetic field required for this. Magnetic field is also needed to confine the charged particles into a beam of small cross-sectional area. When particles collide at high energies, the energy of the collision is converted into matter in the form of new particles produced in the collisions. This follows Einstein's mass-energy relation E = mc square, according to which mass and energy are interchangeable. As the scientific inquiry into the structure of matter and the evolution of early universe progresses, collisions at higher and higher energies are studied. Accelerators have become bigger and bigger in size and capacity. The Large Hadron Collider LHC at CERN is the world's largest and most powerful particle accelerator. It accelerates and collides hadrons and heavy ions at very high energies. Hadrons are composite subatomic particles formed by quarks held together by gluons. Protons and neutrons are hadrons with 3 quarks each. Neutrons cannot be accelerated because they have no charge. LHC is a particle collider. Colliders are accelerators which produce collisions among accelerated charged particles. Other accelerators direct the accelerated beams of particles to fixed targets. The LHC project is implemented in an underground tunnel in which CERN was earlier operating the Large Electron Positron Collider (LEP). While LEP accelerated charged particles up to 100 GeV of energy, LHC is designed to produce accelerations up to 7 tera electron volts, a 70-fold increase. CERN started the LEP in 1989. In 2000, LEP was closed and the tunnel was made available for the LHC project. This huge tunnel of LHC is 27 km in circumference and lies beneath the surface at the Switzerland-France border near Geneva. LHC being a particle collider, there are 2 beams of particles traveling in 2 circular rings. Particles are accelerated in opposite directions in these 2 rings. There are 2 transfer tunnels, each 2.5 km in length, connecting the LHC to the CERN Accelerator complex. The accelerator complex has linear accelerators, proton synchrotron booster, and super proton synchrotron. Protons are pre-accelerated in the accelerator chain up to 450 GeV of energy before they are given to the LHC for further acceleration. The LHC takes around 20 minutes to accelerate protons from 450 GeV to 6.5 tera electron volt of energy. The actual acceleration of particles in LHC takes place in RF cavities. 16 RF cavities are housed in 4 cylindrical modules called cryomodules, which help them to operate in the superconducting mode. The total accelerating potential is 16 megavolt, and the RF cavities are tuned to oscillate at 400 MHz frequency. LHC is the largest cryogenic system in the world. Cryogenics is the branch of physics that studies the production and effects of very low temperatures. At LHC, the velocity of charged particles can reach to very high values. In order to keep these particles into circular paths, a very powerful magnetic field of up to 8.33 Tesla is needed. Thousands of electromagnets are placed around the LHC tunnel to produce this very large magnetic field. In an electromagnet, magnetic field is produced by electric currents. A large current of 12,000 ampere is needed in the coils of the electromagnets to produce the very large magnetic field required at LHC. Coils must be of superconducting material to avoid overheating when such very large currents are flowing through them. The niobium titanium wires of the electromagnets coils should be kept at very low temperatures to reach the superconducting state. The LHC superconducting magnets are therefore maintained at minus 271.3 degrees Celsius or just 1.9 Kelvin by a closed helium circuit. This is colder than outer space. Gaseous helium at atmospheric pressure changes to liquid state when cooled to about 4.2 Kelvin. If cooled below 2.17 Kelvin, it changes to the superfluid state. Superfluid helium is an efficient thermal conductor. This makes liquefied helium as the best refrigerant for cooling the LHC's superconducting systems. 120 tons of liquefied helium is used for maintaining the LHC tunnel at ultra low temperatures. LHC is also the biggest operational vacuum system in the world. In order to avoid collisions between accelerated charged particles and the air molecules, a near perfect vacuum should be maintained in the LHC rings. Perhaps more challenging than constructing a particle accelerator is designing and fabricating the particle detectors that will detect and record the large number of collisions taking place. In the Large Hadron Collider, the two oppositely moving high energy particles are made to collide at 4 different locations along the ring. These locations correspond to the positions of 4 particle detectors: ATLAS, CMS, ALICE and LHCb. ATLAS is a general purpose particle detector. It is the largest particle detecting setup at the LHC. Collisions of particles traveling at energies up to 7 trillion electron volts and speeds up to 99.99999% that of velocity of light take place at the center of ATLAS. A billion such collisions take place every second. 1 in a million collisions are chosen for further study. A large data analysis system consisting of 40,000 CPU units is used for analyzing the data generated by these collisions. ATLAS can detect a wide range of signals, and it is intended to detect any new process or any new particle arising from the collisions. ATLAS can measure mass, charge, spin, energy and momentum of any new particle detected. CMS is also a general purpose detector like ATLAS, but it uses a different technical solution and different magnet system design. CMS records collisions up to 40 million times per second. Most of the products in these collisions are unstable and they rapidly transform into other particles. With the help of strong magnetic fields, the trajectories of these particles can be analyzed. CMS is especially designed to detect particles called muons. The CMS experiment is one of the largest scientific collaborations in history, involving 5,500 scientists, engineers, technicians and students from 54 different countries. ALICE and LHCb are detectors designed for specific inquiries. ALICE is dedicated to the study of heavy ion physics. It studies the phase of matter called quark-gluon plasma. Collisions at LHC generate temperatures 1 lakh times hotter than the center of the sun. At this extremely high temperature, similar to that existed just after the Big Bang, matter forms a special state called quark-gluon plasma. The LHCb experiment specializes in studying the differences between matter and antimatter by investigating the beauty quark or B quark. The biggest achievement of LHC so far is the discovery of Higgs boson in 2012. In 1964, British theoretical physicist Peter W. Higgs proposed a mechanism by which fundamental particles acquire mass. He proposed that space is filled with a scalar field called the Higgs field. When fundamental particles interact with this Higgs field, they acquire mass. When collisions of high energy particles take place, there will be disturbances produced in the Higgs field. The vibrations of Higgs field will produce a new particle with zero spin, that is the Higgs boson. Experiments at ATLAS and CMS detectors of LHC confirmed the existence of Higgs boson with a mass of 125 GeV among the products of numerous proton-proton collisions. On July 4, 2012, the CERN scientists officially announced the discovery of Higgs boson. This is a momentous discovery it confirms the standard model as the authentic theory of all non-fundamental particles. It also eliminates our understanding of events immediately after the Big Bang. Experiments at LHC have made tremendous progress in understanding the properties of Higgs boson. Its properties may give useful indications about physics that lies beyond the standard model. Extensive studies are also made into different ways in which Higgs boson decays into other fundamental particles. The rare decay of Higgs boson into bottom quarks is one of them. The production of Higgs boson along with top quark is also studied. LHC experiments have also led to the discovery of new particles like pentaquarks. Once the third run of the LHC is completed in 2026, the stage will be set for the High Luminosity Large Hadron Collider or High Luminosity LHC, which will be operational from 2029. The new accelerator will have a luminosity almost 10 times that of the current LHC. Luminosity is proportional to the number of collisions occurring in unit cross-sectional area in a given time. Higher the luminosity, more is the number of collisions and more will be the data generated for further analysis. The now running LHC and the future high luminosity LHC experiments are designed to expand the frontiers of our understanding of fundamental physics. Physicists are actively looking into frontier areas of research like antimatter, dark matter, supersymmetry, and many more.